The rocket is propelled by a jet of water leaving the nozzle of the bottle. To create the maximum flight time, we needed to find the optimum water fraction. To achieve this, we need a large impulse. If the rocket doesn't have enough water, there will not be enough thrust produced, because the impulse will be small, as the mass of the water is relatively small. If the fraction of water is too large, the rocket will be too heavy to achieve sufficient acceleration at launch, where thrust is highest. We found that the optimal water fraction for a 2-litre bottle is to be around 0.45. The fins on the rocket and the nose cone control directional stability. Directional stability is the ability to be able to return to its initial equilibrium position after a disturbance. Using Unity simulations, we found that the further down the fins are, the more stable the rocket's flight path. This is due to the higher leverage caused by the increase in perpendicular distance, so the rocket returns to equilibrium faster. As you can see on the first video, the optimum fin positions aren't attached to the rocket. It would be impractical to reproduce this in practice. Therefore, the fins will be a bit higher on the real rocket. When we tested fin shapes, the rectangle was the least effective as the drag of the leading edge was so large, causing a maximum height of only 18.6 meters. We found that the cut delta and the parallelogram had the best flight time. They both caused little drag and worked well in low wind, but the cut delta fin outperformed in high wind, so we've chosen to use this shape. The parachute will increase air resistance during the fall, therefore reducing the terminal velocity. This increases the time in the air, but making it too large will mean it takes too long to deploy, so the rocket has lost too much altitude before deployment. We found that the ideal surface area for the parachute is as large as possible, as this decreases the speed of descent. However, we do not want to trust the Unity simulations due to the possible inaccuracies in deployment time, as the larger the parachute, the longer the deployment time. To find the true optimal parachute size, we will do real-world drop tests with different size and shape parachutes. To gain an appreciation for individual parts, we tested each variable separately. This showed us how different design choices would impact the overall design. We used Excel to do precise calculations so that we could estimate the values to try in Unity. Once an optimum value is found for all the aspects, we combined them but continued to adjust the designs to ensure that one component did not negatively impact the others. We also considered the real-world consequences, such as the weather. In Unity, we use perfect weather conditions to start, and then we worsen the weather conditions to test the rocket's durability. The main reason was to ensure it lands in the 50-meter box. We also need to consider the fin placement realism. As you saw earlier, the fins will need to be a bit higher than the ideal to be able to work. We also accounted for human error, as we are building it ourselves. It is unrealistic for us to make a perfect rocket, such as the egg being at the center point. To account for this, we lowered the build quality in Unity. We've also decided not to add complex systems such as rocket rifling and more than one parachute. The position of the egg is vital, as we need it to be as high as possible whilst maintaining its security. To do this, we will be padding the exterior of the egg to help dissipate any high gravitational or impact forces.